Dark openings might be among the most fascinating and mysterious phenomena in the universe. They are enormous entities, incredibly powerful, yet essentially invisible to us. A dark opening can be anywhere from 2 to 4 million times the mass of the Sun. Over the past few decades, our understanding of them has evolved dramatically, from knowing almost nothing to getting much closer and more detailed insights. Recently, scientists, including Michio Kaku, have made groundbreaking discoveries, revealing what lies inside these cosmic enigmas. This new information sheds light on the details that science may have previously missed. Join us as we delve deeper into dark openings and uncover their secrets. Space is vast and full of surprises. Before we explore what Kaku has discovered, let's first revisit the basics. Although many of us have some understanding of dark openings, there are still many unknowns. In 1916, Albert Einstein published his general theory of relativity, which predicted the existence of dark openings. At that time, dark openings were purely theoretical. It wasn't until the 1960s that scientists found actual evidence for their existence. During this period, astronomers were studying the Cygnus constellation and spotted a strange, extremely bright blue star emitting X-rays. This star wasn't just a distant object, it was orbiting a massive, mysterious entity. Further investigation revealed that these X-rays weren't just floating around on their own, but were being pulled into this object. That was the first real discovery of a dark opening, named Cygnus X1. This discovery was monumental because it provided concrete evidence that dark openings do exist, confirming Einstein's theory wasn't just imaginative speculation. But this was just the beginning. After the discovery of Cygnus X1, researchers started searching for more dark openings. It's estimated that there could be more than 100 million dark openings in the Milky Way galaxy alone. However, because they are so incredibly difficult to detect, we still lack a precise number. Still, it's clear there could be millions of these massive objects within our galaxy, making them even more important to study. The main concern with dark openings is always going to be gravity. Their gravitational pull is so intense that anything that gets too close gets pulled in, eventually shrinking down to a singularity. In simpler terms, dark openings act like cosmic vacuum cleaners that suck everything in. One of the scariest parts of dark opening research is understanding what happens if something were to fall into one. The process is slow, but inevitable. Anything that enters a dark opening will eventually be crushed into a singular point. This process would happen gradually, and the person or object would likely die before it fully reaches the point of no return. In fact, no one should intentionally approach a dark opening, but since they are scattered throughout space, they raise important concerns. The closest dark opening to Earth is around 1,500 light-years away, which might seem distant but is still close enough to warrant concern. In 2021, scientists captured the first clear image of a dark opening, the M87 dark opening. This dark opening was photographed over several nights, and each image provided more evidence about its structure. Researchers had to stitch together individual photos to form a complete picture, revealing that dark openings aren't just simple, single points of nothingness as many believe. Things are far more complex. To reach the true singularity of a dark opening, one has to pass through 3 distinct layers. The first layer is known as the event horizon. This is the point of no return. Once something crosses the event horizon, it's sucked straight into the dark opening with no chance of escape. It only gets worse from there. The second layer is the photon ring, where light itself gets trapped and cannot escape due to the gravitational force. Finally, we reach the third layer, the singularity, where everything that enters the dark opening gets compressed to an infinitely small point. At this point, the laws of physics as we know them break down, and we can't predict what happens next. What makes studying dark openings so difficult is the fact that each one is unique. While they generally follow this 3-layer concept, their specific functions can be vastly different. If this were any other phenomenon, researchers could simply use telescopes to study them in depth. However, with dark openings you can't do that. Researchers can only study dark openings indirectly by observing the radiation they emit and the gas and dust that surround them. Sending a probe into a dark opening is impossible because once anything crosses the event horizon, it gets pulled straight into the singularity, where it's crushed to nothingness. This obvious issue leaves scientists with no choice but to study dark openings in a more indirect, two-dimensional way. Even though dark openings have 3 distinct layers, traditional scientific methods don't apply in their study. To make matters worse, each dark opening presents unique challenges, combining the strange physics of black holes with the breaking down of laws when investigating inside them. One of the most compelling theories about how dark openings form suggests they come from dying stars. When a star exhausts its fuel, it can no longer produce enough energy to counteract the powerful force of gravity pulling inward. As a result, the star begins to collapse on itself, shrinking down denser and denser. If the star is massive enough, this process can continue until it becomes a singularity. To understand the nature of dark openings, NASA researchers turn their attention to the center of the universe, specifically the M87 galaxy. They observed a swirling vortex of incredibly hot hydrogen gas spinning at an astonishing speed of 1.2 million miles per hour. Normally, such intense spinning would cause the gas to fly apart, but it doesn't. Researchers concluded that a massive object must be at the center of this galaxy, preventing the gas from scattering. This enormous object weighs as much as 2 to 3 billion suns, making it a dark opening. But that's not the only theory. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to provide a better description of spinning dark openings. Kerr showed that a spinning dark opening wouldn't collapse into a point, as once thought, but would instead form a ring of fire or a thin disk. This disk spins so rapidly that its radiating forces prevent it from collapsing. This spinning disk of matter is known as the ergosphere, and it's the region surrounding a dark opening where the laws of physics begin to break down. The most fascinating element of Kerr's solution is the prediction of an Einstein-Rosen bridge, also known as a wormhole. A wormhole is a hypothetical tunnel through spacetime that connects 2 distinct areas of the universe, or even 2 parallel universes. The idea is that if one were to fall into a dark opening rather than being crushed to a point, they could instead be sucked into a passage, exiting at a white opening in another universe. To understand how this works, we need to dive into the concept of spacetime in Einstein's theory. Space and time are not separate entities, but are interconnected. In our universe, objects with mass twist the very fabric of spacetime, creating gravitational fields that cause other objects to move towards them. Imagine placing 2 points on a flat sheet of paper and defining a boundary between them. This serves as a basic model of how objects travel through spacetime. Now, what if you could fold the paper in half, creating a shortcut between the 2 points? This is the fundamental idea behind a wormhole, a shortcut through spacetime that connects 2 distant points almost instantly. Wormholes aren't just a concept from science fiction. They are, in fact, a prediction of Einstein's general relativity, though they have never been observed directly. The reason is that wormholes are inherently unstable and would likely collapse almost immediately. However, the existence of an Einstein-Rosen bridge suggests that black holes are not merely vacuum cleaners sucking everything into them but could also act as gateways to different regions of spacetime. Could we ever use a wormhole to travel through space? Unfortunately, at least for now, the answer is likely no. Even if we could stabilize a wormhole, it's improbable that we could use it to travel faster than light. Einstein's theory of special relativity states that the speed of light is an absolute limit on how fast anything can move through spacetime. Nonetheless, the study of wormholes and black holes as potential pathways to different parts of the universe, or even to other times, has fascinated physicists for decades. One of the most intriguing concepts in this area is the Kerr wormhole, named after mathematician Roy Kerr, who first described it using Einstein's equations of gravity. This kind of wormhole could theoretically serve as a passage through spacetime that connects 2 far-off locations, such as 2 different universes or even different times within the same universe. The concept of the dog-shaped wormhole is often imagined as a ring-shaped gateway, similar to the mirror in Lewis Carroll's Alice in Wonderland. Stepping through this ring might transport an explorer to another universe or even a different time, where the laws of physics could be vastly different from what we are familiar with. However, at its destination, the nature of what they encounter could simply appear as ordinary. While the idea of wormholes for interstellar travel or time travel is undeniably exciting, it remains a subject of debate among physicists. Some argue that wormholes, particularly dog-shaped ones, may be unstable or impossible to cross due to intense radiation and subatomic forces surrounding their entry points. Critics point out that Einstein's equations of gravity, which describe wormholes and black holes, do not account for quantum forces that govern radiation and particles at a microscopic level. To fully understand these phenomena, a different theory is needed, a theory of everything that unifies gravity with quantum mechanics. One such theory being explored is the superstring theory, which aims to do just that. Superstring theory suggests that subatomic particles are actually tiny vibrating strings, and the universe itself is an ensemble of these strings. Like different musical notes, the vibrations of these strings correspond to different particles. One fascinating aspect of superstring theory is that as a string moves through time, it warps the fabric of space-time, creating black holes, wormholes, and other intriguing structures. This means that superstring theory not only unifies Einstein's theory of gravity with quantum mechanics but also explains many of the strange phenomena we observe in the universe. However, superstring theory relies on additional dimensions of spacetime that are so tiny that we can't directly observe them. The most precise measurements we can make in our laboratories utilize the 4 dimensions of spacetime: length, width, depth, and time. But what if additional dimensions exist? One possibility is that these extra dimensions are folded so tightly that they remain hidden from us. Imagine a sheet of paper tightly rolled into a cylinder. If you were an ant walking along the surface, you might not even notice the paper is curved. Similarly, the extra dimensions of spacetime in superstring theory could be compacted into tiny circles or twists, imperceptible to us, but still influencing the behavior of the strings that vibrate within them. Another possibility is that these extra dimensions were more apparent in the early moments of the universe during the Big Bang. According to some versions of superstring theory, the universe began with a 10-dimensional spacetime, where all dimensions were equally noticeable. As the universe expanded and cooled, these extra dimensions began to collapse and fold, leaving us with the 4 dimensions we observe today. If this scenario is correct, we might one day detect traces of these extra dimensions around us. The mathematics involved in superstring theory is incredibly complex and has led to entirely new areas of math that were previously unexplored. However, solving the problem of quantum black holes has proved to be a challenging task. While many physicists have worked on this issue, no one has yet succeeded in fully solving it. Renowned physicist Edward Witten from the Institute for Advanced Study at Princeton has referred to superstring theory as 21st century physics that accidentally fell into the 20th century. Last year, several independent groups of physicists made a significant breakthrough. They discovered that string theory could fully address the problem of a quantum black hole, at least in 2 dimensions, not 10. Many physicists believe it is only a matter of time before someone solves this puzzle, given the right conditions. Until then, it's still too early to book tickets for intergalactic travel or time-traveling expeditions. Despite all this, one thing is clear: there are far too many questions and even more answers to these mysteries. Physicist Michio Kaku has explained that the issue of countless answers isn't unique to string theory. In fact, many great theories have an infinite number of possible solutions. For instance, Newton's laws can predict the motion of everything from rocks to rocket ships, but you first need to specify what you're trying to explain before you can predict its motion. These specific conditions are called initial conditions. Similarly, in string theory you need to tell the theory what it's describing. But unlike other theories, the initial state in string theory is the Big Bang itself. This means we need to specify the conditions of the Big Bang at the moment it was created, which as of now remains unknown.